How's it going, guys? Today in this video, we're going to begin actually module 2. We're going to start with module 2.1, obviously. So if you haven't already, there's a little warm-up in the very first page of your packet. One of the very first page, like page 4 of your packet. If you haven't done it, go ahead and do that. Pause the video and do it. I think I've said in previous videos, I know I've said to my students a lot that this right here, this function right here, the generally form of multiple transformations. It's very, very important for this course. We're using it all year long. So the sooner you have this down, the sooner you know it very well, the easier your life will be in this course. So go ahead and pause it. Try to do this yourself. And in a quick second, I'll show the answer and we'll move on. Okay? So this is what you should have gotten. For the warm-up, it's the same transformation we talked about pretty much all of module 1. It's what you just had a test over. And that's what the transformations are going to be. It's going to be the same thing in this course, in this module, I mean. It's going to be the same thing throughout the rest of the year. So get comfortable with it. Like I've said many, many times, we're going to be using this all year. All right? But for today, we're going to be using a different parent function. In this case, it's going to be the absolute value function. So the absolute value, which can be written as that bar x bar, represents the distance between x and 0 on a number line. And since we're dealing with distance, and since the absolute value tells you what the distance is, the absolute value has to be non-negative. And that word non-negative is important. We cannot use the word positive because that implies we cannot use 0. Well, you can say I went 0 distance, right? You can say I went 0 units. That still makes sense. And 0 is not positive, so you have to make sure we use the word non-negative. All right. So there'll always be there's always going to be 2 points on opposite sides of 0 that are the same distance away. For example, 5 and negative 5, they're both 5 units away from 0. So the absolute value of 5 is 5, and the absolute value of negative 5 will also be 5, since negative 5 is only 5 units away from that 0. All right. So the absolute value, we can actually define it piecewise, which just means we're breaking up an equation into two different parts for different parts of the domain. It's a little above the course, so we're not going to touch on it too much. But in other words, what that piecewise function is saying is that when x is positive, or when x is greater than or equal to 0, the function returns the same number. So if you plug in an x value into this piecewise function or into an absolute value function, if that x is positive or non-negative is actually a better word to say. It shouldn't say positive, it should say non-negative. So if x is non-negative, the function returns the same number. All right, so if you plug in 5, you're going to get the same number of 5. You plug in 6, you're going to get 6. You plug in 0, you're going to get 0. But on the opposite side, if x is negative, you're going to get the opposite of x. For instance, if you have negative 2 for x, you're going to get the opposite of that, which is 2. You have negative 3, you're going to get 3. You get negative 4, you're going to get 4. You're getting the opposite of it. So what we're going to do now is we're going to complete the table, and this table is for f of x equals the absolute value of x, just to clarify. All right, that's what this table is for. So when x is negative 8, we have a negative number, so we're going to get the opposite of x. So when x is negative 8, we get 8, the opposite of x. When x is negative 4, that's still negative, so we're getting the opposite of x, that's 4. When we have 0, 0 is non-negative, or in other words, it's positive or 0, so we get the same number of 0. When x is 4, it's positive now, so we get the same number of 4. And when x is 8, we get the same number since it's positive, or rather it's non-negative, so we get 8. And I know the word non-negative is kind of weird. It sounds like kind of like an unnecessary word, but it is necessary because, like I said, 0 is not positive. So we have to use the word non-negative to include that 0. All right. So now what we're going to do is we're going to graph this parent function f of x equals the absolute value of x. And we're going to do that by plotting the points we just found. So negative 8, 8, negative 4, 4, 0, 0, 4, 4, and 8, 8. And what this is going to look like is just a big Z, so not a Z, but a big V, because that's essentially what it is. Just one big V, straight lines to the vertex, and then another straight line shooting out the other way from the vertex. So we're going to go ahead and look at this graph and kind of break it down a little bit. So the graph f of x equals the absolute value of x that's symmetric about the y-axis, or in other words, it has an axis of symmetry on that y-axis. And remember, if you have an axis of symmetry on that y-axis, it's going to be even. It's an even function. All right, if you fold it over the function over the y-axis, they go right on top of each other. So that's what makes it an even function. The domain of f of x equals x. That's going to be, if you look at the graph, we hit every single possible x value, right? Every single possible real x value. That function on that we drew is going up and to the left forever, and up and to the right forever. It's going diagonal both ways, so it's going up and to the left, up to the right forever. So over an infinite amount of time, or however you want to say it, we're hitting every single real number. We're going to the left forever and to the right forever, so we're hitting every single possible real number. So instead of real numbers, you could also say from negative infinity to positive infinity. It means the exact same thing. However you want to think about it, however you want to write it, it's okay. But that's what it is. The set of all real numbers, or from negative infinity to positive infinity. The range of f of x equals x. That's going to be a set of all non-negative real numbers, which is really just a very complicated way of saying 0 to positive infinity. It's the same thing from 0 to positive infinity, including the 0. It's still a set of all non-negative numbers, non-negative real numbers. And we can see on this graph that our smallest point is at 0, 0. Our smallest y value is 0. And this graph is going up forever. So our range, or every single possible y value, is from 0 up to positive infinity. All right, here, these aren't doing anything to get rid of them. This one, we're going to be kind of looking at the what are they called? The parameters. Sorry about that. We're going to look at the parameters and the transformations, and we're going to see how they actually affect the graph. So on number 1, we have g sub 1 of x equals absolute value of x, all plus 6. So actually, before we actually break this down or look at these transformations, I want to give you guys, I don't know if you guys can hear all those trumpets. I don't know what's happening outside my room, outside my classroom. I'm sorry about that. I'm going to pause this video until that calms down. Okay. Sorry about that. Anyway, back to what I was saying. I'll give you guys the general equation for the absolute value function. And it's going to look very similar. And that's because it's the exact same thing as the general transformation rule that we saw in the warm-up. And that's because it basically is the same thing, except we're trading the parentheses for the absolute value signs. All right? You see that's the exact same thing. A times the absolute value of 1 over b times x minus h, close the absolute value, plus k. That's our general transformation for the absolute value function. All right? So we're going to compare all these functions we have down below with that general equation, which you're going to have at the end of this page, I think, in your notes. But that's what it's going to be, so we can refer back to it. So number 1, we have the absolute value of x plus 6. That plus 6 is we're adding it to the absolute value outside of the absolute value. So that looks most like this k we have over here. So that means our k is 6. And when our k is 6, we're going up by 6 units. All right? So if we're going to graph this function, we're going to go here to our parent function that we have already listed out. And the only thing that's changing is we're taking this graph and we're sliding it up 6 units. So draw your B as best as you can, It doesn't need to be perfect. As long as you know that the transformation is just going to be 6 units up. You're going to take the vertex, go up 6 units, and that's what it should look like. For g sub 2 of x equals absolute value of x minus 4. In this case, I can do it in a different color. So in this case, we're subtracting 4 from the absolute value. That's still going to coincide with this k. It's still kind of related to it, right? It's in the same form. The absolute value function minus your k, or adding your k, right? It's still outside of it. So it's still going to be our k value, in this case of -4. And when our k value is -4, we're going down by 4. Remember, this is still going to be the same transformations that we saw in the warm-up. Our a, b, h, and k are still going to affect the function the same way they did before in the previous chapter. So our k's are still our vertical translations up and down. So now if we're going to graph this function, we're going to take our f of x parent function and just slide it down 4. And same thing, draw your V as best as you can. It doesn't need to be perfect, as long as you know that the only transformation that's happening is you're taking it and moving it down 4 degrees. All right, number 2, we have g sub 1 of x equals the absolute value of x minus 3, then all that inside the absolute value function. So if we're going to take this and compare it to our general equation we have for the absolute value function up above, that x minus 4, x minus 3, we're subtracting 3 from the x value inside of the absolute value function. So to me, that looks like it's most, it looks closest to this x minus h, right? It looks closest to that. So that means our h is going to be our positive 3, right? X minus the h value, x minus your h value of 3. So h is 3. Another way to think about it is you have x minus 3 here in the equation. Just flip the sign, that's your h value. Whatever way you want to think about it, just know your h is 3 because in the regular equation, the general equation, it's x minus your h value. So our h is 3. Our h's still tell us our horizontal translations, left to right. So we're going to the right by 3. So we're going to take our function, go over 3, and our function will look something like that. Like I said, it doesn't need to be perfect, as long as you know that the only transformation that's happening is you're sliding to the right by 3. All right, and then for g sub 2 of x equals the absolute value of x plus 5. In this case, the x plus 5 is still inside the absolute value function, so that plus 5 is still going to be our h. Or sorry, not our plus 5, but the x plus 5 is going to be the h parameter that's changing the function. So we just need to figure out what our h is going to be. So remember, the form is x minus h. So basically, x minus h has to equal x plus 5. If you solve this out, I don't know why I put x plus h, but it should be x plus 5. So if you had x minus 5, that's going to give us our x plus 5. X minus negative 5 is x plus 5. All right, I'm not going to spend that much time on transformations anymore. Sorry, negative 5, not positive 5. Yeah, like I said, I'm not going to spend too much time explaining transformations anymore, just because that's the previous module, previous chapter. If you're having some trouble with that, go back, watch the old videos, do some extra problems, do what you need to do, because like I've said like 1,000 times now, this stuff is not going away. We're dealing with it pretty much all year. All right, so back to the graph. We're going to graph this function. It's the same thing. We're going to graph the parent function, the one at 0, 0, the vertex at 0, 0, move it to the left by 5. And you're going to get something like this, more or less. It's not perfect. It doesn't need to be. As long as you know the only transformation that's happening is you're taking the parent function, it's sliding to the left by 5. All right? So let's keep on going. This page, and this slide over here, we're just going to continue on. In this case, we're dealing with stretches, compressions, and reflections. So on number 3, we have g sub 1 of x equals 1 over 4 times the absolute value of x. So if you compare it to your transformation, your general transformation of the absolute value function, what I wrote in the previous slide, we can see that that 1 over 4 is related to our a. So our a is 1 over 4. So that means you have a vertical compression by 1/4. And when you have a vertical compression, I like to think about it kind of like a Coke can. If you have a Coke can, and you take it and you kind of vertically compress it, or you push down on it, that Coke can is getting flatter, right? And that's exactly what's going to happen to our graph. If you take our graph and you vertically compress it, you push down on it, it's going to get flatter and more wide. And that's exactly what's going to happen to this graph. And like I said before, it does not need to be perfect. Nothing I'm drawing is even close to that. As long as you know that when your A is, we have a vertical compression, you're going down and you're getting wide. All right, that's the most important thing we're trying to take away. For g sub 2 of x, that equals negative 3 times absolute value of x. So that negative 3 is still going to be our a. So our a is negative 3. And that's going to be a vertical stretch, but it's also going to be a reflection across the x-axis, or a vertical reflection, right? Our a's deal with our y's, so that's why it's a vertical stretch and a vertical reflection, or in other words, a reflection over the x-axis, right? It reflects vertically, it's going over the x-axis. Okay, so when you have a vertical stretch, the way I think about this one is if I have some Play-Doh and I kind of pull on it vertically, I stretch it out vertically, that Play-Doh in the middle is getting much thinner, right? Much thinner and much more narrow. And that's exactly what's going to happen to our graph. You grab the parent function of the graph, you stretch it vertically, you're going to get a much narrower graph, but we're also reflecting across the x-axis. So just draw your function reflected over the x-axis and narrower than the parent function. It doesn't have to be exactly at a factor of -3. It's not that important. We're going to deal with that later. The most important part is you know the general look of the function. All right, for number 4, g sub 1 of x equals absolute value of 1 over 4 times x. Since that 1 over 4 is inside parentheses and we're multiplying the x with it, that's going to be going with our 1 over b. So that's saying 1 over b equals 1 over 4, or it's just that our b is going to equal 4. When our b is 4, we have a horizontal stretch. And if you stretch something horizontally, you grab something, you stretch out left to right, you're making that thing wider, right? You're making it wider, and that's how our graph is going to react to. If you grab the parent function and you stretch it out horizontally, it's going to become a much wider graph. Say something like that. That's not even close to being right, but whatever. As long as you know that when b is greater than 1, a positive number is if b is greater than 1 in a way that it makes the graph horizontally stretch, there we go, it's going to be wider than the parent function. All right. Now for the second part of number 4, g sub 2 of x, that equals the absolute value of -4x. Our 1 over b, equals -4. If you solve for b, you get b equals -1/4. That's exactly what we have. B is equal to -1 over 4. That gives us a horizontal compression. And on top of being a horizontal compression, since it's negative, you're reflecting horizontally. If you reflect horizontally, you're reflecting over the y-axis. And if you reflect over the y-axis, in this case, it's not going to do anything just because, remember, it's an even function. That means you're symmetric over the y-axis. So if you reflect over it, it's not doing anything. But you'll see in other examples that there is a reflection over the y-axis. It can't affect the graph. It just happens in this case. It's not going to do anything. Anyway, when we have a horizontal compression, you're taking a graph and you're squeezing it together. If you take this graph and squeeze it horizontally, that graph is going to become more narrow. So, like I said, every single time a graph, it doesn't need to be perfect. You just need to show a horizontal compression, the general shape of it. It's going to be narrower. If you press it horizontally, it'll be narrower, like we have there. And at the same time, it should be a reflection over the y-axis. You're not going to see it. It's not going to do anything in this case, but in other cases it will. But just know if b is negative, you do have a horizontal reflection. All right. So we're going to keep going. The transform vertex at this point. So something to pay attention to is that our vertex for this absolute value is still 0, 0. And remember in the previous chapter, we talked about how at the vertex of 0, 0, your transform vertex will be hk because you plug in 0 for b and 0 to a for our transformation rule. The bx and the ay cancel out. You're just left with hk. Right? We talked about that in the previous chapter. And these transformations are going to be the exact same. All right? It's the exact same as the warm-up, exact same thing you saw in the previous chapter. It's not going to change. Only thing we really did was just add these horizontal lines for the absolute value. Vertical lines for the absolute value instead of using the parentheses. All right, and this page right here, so I think it's at the top of the next page in your notes. This is just a little table kind of summarizing everything we need to know about graphing absolute value functions. The parent function, f of x equals absolute value of x. Our transform function is that function right there. If your original point is xy, the transform point is bx plus h, comma ay plus k. Or how I like to think about it is that that's the transformation rule. Just T rule for short. Our transformation rule is bx plus h, comma ay plus k. Okay, so now we're going to work a couple of examples. Example 3, we're given the function g of x. We need to find the vertex of the graph, list the transformations in words, write the transformation in the form xy equals, or xy goes to bx plus h, ay plus k, and then we're graphing it. All right, so first we need to do is we need to figure out our A, B, H, and K. Even if they didn't give us that A, B, H, and K, that should always be the first thing we do. If you have your parameters laid out, it makes everything else that much easier. So here we see our our A is 4. We don't have a B, so it's 1. Our H is a positive 5. And our K is negative 2. Remember our vertex, we just talked about that, it's HK. So it's 5, negative 2. And our transformations, that's going to come from our parameters A, B, H, and K. Our A is 4, so we have a vertical stretch. Our H is 5, and that means we're going to the right by 5. And our K is negative 2, that means we're going down by 2. So our transformation rule, Bx plus H, we don't have a B, so just X plus our H value of 5, comma, AY plus K, 4Y minus 2. So that's our transformation rule. And what we do with that transformation rule is we're going to plug our reference points into that transformation rule. Remember, this is in the form XY. Plug the X into the X, the Y into the Y. And when you solve that out, that gives you your new transform point. And if you pay attention to these the reference points, I just want to point out that it actually doesn't matter which points you use. The only one you have to use is 0, 0. You have to know what's happening in the vertex because that's our turning point. We need to know what's happening there, and we need to know what's happening on both sides of the vertex. Or in other words, we need to know what's happening to the left of the vertex, and we need to know what's happening to the right of it. So that's what we chose, negative 1, 1, and 1, 1. That's a point to the left of the vertex and a point to the right of it. But we could have chosen negative 2, 2, and 2, 2, negative 3, 3, and 4, 4. It doesn't matter, as long as you have 1 point to the left and 1 point to the right of that vertex, including the vertex. Anyway, now we're going to figure out what our transform points are. We're going to plug these points into the equation. We get negative 1 plus 5, comma 4 times 1 minus 2. Just plug in negative 1, 1 into the equation. And when you solve this out, you get 4, 2. Negative 1 plus 5 is 4. 4 times 1 is 4, minus 2 is 2. For 0, 0, we talked about this. Our 0, 0 is our vertex. So we just end up getting 5, negative 2. And if you're wondering why, just plug in your 0, 0 into your equation and see what you get. You're going to get the same thing, 5, negative 2, 2. And you're going to see how the x and the y's cancel out. For 1, 1, we're going to plug in our x and y into the equation. 1 plus 5, 4 times 1 minus 2. You plug that in, we get 6, comma 2. All right. So now we have our reference points, or sorry, transform points. We're going to go ahead and plot them and figure out our new transform function. So we have 4, 2, 5, negative 2, and 6, positive 2. And this is not going to be very pretty. My smartboard isn't very synced. But it's going to look something similar to that, right? It's going to be a narrow V because we have a vertical stretch, and we move the vertex to the right 4, and sorry, to the right 5 and down 2. All right. And now for number 2, we're going to do the same thing. Figure out our parameters. Our A is 1. Our B, remember we flip it 1/3 because it's 1 over B equals 3, so it's 1/3. H is 2. K is 2. Our vertex is HK, 2, 2. We're going to go about this problem a little faster now. Our transformations, our A does nothing. Our B tells us we have a horizontal compression. H comes for shorts. H, we go to the right 2. K, we go up 2. Our transformation rule is going to be 1/3 times X, or Bx, plus our H of 2, comma AY plus K, or just Y plus 2. And now if we see here with our, what are they called? The reference points, there we go. Our reference points in this case, they're not the regular negative 1, 1, 0, 0, 1, 1. We still have that 0, 0 because we need to know what's happening at that vertex. We need to know what's happening at that turning point. So that's always going to be a point. It's always going to be one of our reference points because we need to know what's happening at that turning point. But that negative 6, 6 and that 6, 6, those are different than negative 1, 1. And that's because we have this fraction in the transformation rule. If we try to plug in -1, 1, you end up getting fractions and dealing with fractions. You know, we're already doing math. Make your life as easy as possible. Don't deal with fractions if you don't have to. Work smarter, not harder. I know you've heard that 1,000 times. That holds true in math as well. So what we want to do is we want to choose points that will get rid of that denominator. That's what we chose, -6. All right, -6. If you multiply that with 1/3, we'll see right here, we have 1/3 times our x value of -6 plus 2, comma 6 plus 2. If we try to solve this out, see this 1/3 times that -6, that's going to actually cancel each other out, and you're left with -2. Right? Just a quick reminder of some fractions. So -1/3 times, or sorry, 1/3 times -6. So 1/3 times -6. We can rewrite this as 1/3 times -6/1. And this 3 and -6 actually cancel each other out. -6 divided by 3, you can cancel stuff out like that if you're multiplying. This gives you a 1/1 times -2/1, which is just -2. So that's why we chose -6, because we wanted to get rid of that denominator. All right. So just a quick more examples, because I know some stuff like this on the homework, it's a little trickier. If we had, say, something like 5/7, which I think is actually exactly what you have in the homework, you want to choose something that cancels out the denominator. For instance, like just 7, right? We use 7/1. These 7s cancel out, and you're left with just 5. So you want to choose points that cancel out that denominator, so like multiples of that denominator. All right, hopefully that makes sense. Anyway, go back to our problem over here. You solve this out. You end up getting 0 to +8. 0, 0 is our transformation. It's not our transformation point, but our HK. So 2, 2. And lastly, 6, 6. We're going to plug in our, this would be a 3, our x and y into this equation. And when you do, 1/3 times 6 is 2, plus 2 is 4. 6 plus 2 is 8. So you get 4, 8. We're just going to go ahead and plot these points. 0, 8, 2, 2, 4, 8. Remember, the absolute value is a big V, it's straight lines. So draw straight lines from the vertex out to both of those points. And that's what you get. And for number 3 and number 4, I want you guys to actually pause the video to try that yourself. They're going to be a little harder than this, just because there are some reflections in there. But just get your transformation rule. Let's say your transformations, but get your transformation rule, plug in your x and y into the equation, and just plot those points and plot left to right, and I'm sure you'll get it, all right? So pause the video, try it out yourself. In a couple seconds, I'm just going to flip it to the next slide, and you can compare your answer with mine, all right? All right, so this is what you should have gotten, so your graphs should have looked like. Like I said, those graphs aren't very pretty. My board is completely synced, and I'm not very good at connecting dots, apparently. But this is what you should have gotten. The ones in red are your new transform points. I know my screen was a little different than yours. I don't have the A, B, H, and K, but hopefully you list them out. Just compare what I have here with what you have on your page. If it's the same thing, give the same transform points right here. And your graph looks just like mine. You did great. You did the problem right. Don't stress about it. But if you didn't, rewatch how I did number 1 and number 2. Then come back and try these again and see if you got the same one this time. All right. Anyway, guys, this video is long enough. Hopefully this helped. Yeah.